my phone. I'm sorry. Okay. We're going to do a quick question and answer about ProgramBench. Somebody's playing with their microphone.
That's me. Sorry.
We just put out this paper called ProgramBench. Let's introduce everybody.
Yeah, sure. I'm John. I'm currently worked on SweetBench with past like 2 years ago, and still have been in benchmarking. And ProgramBench is the latest thing. Yeah.
Kilian.
Hey, I'm Kilian. John and me work together on like a lot of benchmark stuff, and also together with Ofir. ProgramBench is the latest one. Very excited about this one.
I'm Jeff, probably the newest newcomer. I worked on Ofir on Sufficiency, sort of a runtime flavor of SweetBench, and super excited to be with everyone.
I'm Ofir. I worked on SweetBench and then a few other things, and now we just did ProgramBench together. So I guess we did SweetBench, and now we're doing ProgramBench. I guess, what did we want to achieve with ProgramBench? Why was it necessary? Why do we think it's a super interesting thing to work on?
I guess I'll start, and then we'll go through. Okay. SweetBench was very long horizon and difficult when it was first created, and now it's not that anymore. So we decided to push those extremes again. For me, I think the most salient difference was a lot of the benchmarks that had come since SweetBench were still focused on pushing the fundamental paradigm of taking a repository that has a bug and then asking models to fix it. If you look at the SweetBench series from like verified to multilingual, multimodal to pro, it's still fundamentally that. So I think a big shift that ProgramBench does is we're really actually focused on coding a repo from scratch. And, I guess I'll let Kilian and Jeff expand on that.
And also just to clarify, I think we're not the first from scratch coding benchmark that's out there. What's different about this framing is that it really gives the agent maximum freedom to implement the program in whatever way it wants, starting with even selecting the programming language that it wants to use. So it's definitely not the case that, like, actually in I think the majority of cases it picked a different language. Is that right?
Yeah, something like that. Yeah.
There's quite a lot of variance also between different models in which language they pick to even implement the program. Yeah. And fundamentally, there's just like every single architectural decision is in the hand of the agent. And it was very much not the case for SweetBench and all the variations of that. So much more a test of like very high level design capabilities of the agent.
Yeah, for sure. I think Kilian touched on this a little bit, but I think ProgramBench exercises much more autonomy. I think there's much less in terms of what's provided to the agent in terms of existing repo level scaffolding. John, Kilian, and I spend a ton of time on kind of like test generation and how do you actually exercise a executable without assuming anything about its implementation. If you think back to maybe things like SweetBench or maybe like some previous like coding from scratch, some of them provide an existing kind of like scaffold that's sort of like fill in the middle rather than like build from scratch. And so kind of like a big part of building ProgramBench was also figuring out how do we evaluate executables kind of in an end-to-end fashion, like more integration tests, rather than kind of staying at the unit test level.
I guess we should have started from this. Maybe, John, can you explain what is a SweetBench task very briefly, and then what is a ProgramBench task? And then I have some follow-up questions.
Got it. Okay, so for SweetBench, just to set the context, you have a GitHub repository, and there's some bug with it. There's some problem with it. The problem is explicitly conveyed via natural language. And it will say like, hey, here's the NumPy repository, but there's some flag that should be exposed that's not being exposed in the issue text. And then the agent is expected to, modify the code base in a way that addresses the tests. So very quickly, the way that we actually collect these task instances is we look online on GitHub for issue PR pairs. So what that means is like the PR actually has a fix and some associated tests with it, and somehow it also links back to an issue. And that gives you the problem statement, which is the issue text, the reference solution, which is sort of the part of the PR that doesn't add tests, and then certainly the tests themselves. ProgramBench is sourced in a somewhat similar way, but the criteria are different. So with ProgramBench, the formulation is you have an executable or like a compiled binary. That's what we mean by program, along with some documentation that is purely usage related. And the model is allowed to probe the executable. It's allowed to invoke it. And the goal is for the model to completely from scratch write a code base that produces a binary that emulates the behavior of the reference. So looping back to GitHub, the change in collection criteria is now you're looking for repositories that build a program or build an executable, but the repo doesn't necessarily need an existing test suite.
So just to ground this in an actual example, Kilian, can you give us an example of a program in ProgramBench and what an agent needs to do to kind of succeed on that specific task in ProgramBench?
Sure. So there's actually a lot of range of programs that we have. There's some extremely tough ones like FFmpeg, which has been developed since maybe like a decade by hundreds of authors. So that's on the kind of tail end of the difficulty spectrum. There's some extremely simple ones, like including the one that was solved so far. There's like very simple terminal helpers, for example. The most important thing, and also how it's very different from SweBench, is that the agent actually has to explore first what to do. This is not like written down in some design document, but the agent has to kind of poke the executable. Maybe it does have a little bit of documentation, like a README, but then it has to, for example, invoke the help flag of the executable, see what all what flags exist, and it has to systematically exercise every single one to collect that information. And for FFmpeg, we do give the agent a few kind of assets that it can use to, for example, test conversion of videos or whatever. So it has to systematically go through these and discover the behavior that it needs to implement.
Yeah, so just to summarize this in one sentence, FFmpeg is one of our favorite tasks in ProgramBench. It's a very, very complicated, it's a huge piece of software for processing video files. And so the agent gets access to FFmpeg. It cannot read the source code. It cannot decompile it. It has to kind of interact with FFmpeg, read the docs, try to understand all the features that FFmpeg has, and then it has to produce a binary that, when compiled, results in something that is identical to FFmpeg, or as close to identical as possible. And then we grade it using our custom-built testing infrastructure. So Jeff, why don't you tell us a bit about how the testing infrastructure works? How do we grade every submitted program?
Yeah, for sure. I maybe like a easier way to contextualize this is kind of maybe talking about SweBench's pipeline and how we got to where we are. I think for folks unfamiliar, SweBench, kind of the way they're able to find kind of test instances is you look at pull requests where the author contributed tests. Basically, the implicit assumption being that the author would have written a test that would validate their change, and so it's a pretty good verification criteria. I think once you start to, want to give agents like open-ended freedom to evaluate test cases, you kind of need a testing framework that's language agnostic. So maybe it only evaluates the executable or kind of does like a bash only interaction. And then two is you also need to make sure that it is comprehensive. I think if we're kind of saying that agents are able to, maybe at some point when they do really well on ProgramBench, if they're able to do well, we need to be confident that these are actual claims. And so the test coverage needs to be really good. And so kind of there's been a lot of like prior works that have kind of used a lot of coding agents to automate a lot of like boring stuff about benchmark creation. Like John, for example, in SweSmith used SweAgent to like really automate kind of synthetic repo setup at scale. I think in our case, we took that a step further and employed it to kind of actually start generating tests behavioral tests for our executables at scale. And so kind of similar to like maybe what you guys have seen with like auto research loops, by kind of tasking these agents with maximizing coverage alongside a bunch of other metrics that we kind of discovered during test generation, you can get kind of existing coding agents to come up with really unique behavioral tests that kind of really really deeply evaluate a executable beyond just like maybe just trying to prompt them to test to executable uphand. And yeah, this turns into really cool test suites. I think we validate these on our actual executables so that kind of we know the instances are actually solvable. And yeah, I think altogether this kind of turns into what a single program bench instance is.
Yeah, so just to summarize, we have 200 tasks, and on average, they have 1,000 tests in the test suite each. And so you get one of these programs, your agent has to try to reproduce it, and then we have 1,000 tests to check various parts of your implementation. So our tests are pretty thorough, but we're actually going to work on making them much more thorough. We're going to make the benchmark even harder. It's very, very hard to completely test a piece of software, and we're going to try to, be as good as we can there. But yeah, we have 1,000 tests and per task on average, and for our main metric, you must pass all of them to get like a passing score on that example. Why don't we go and each mention one library, one program that should we do that, or
do like a speed round?
Yes, speed round, just so we get like good coverage of all the different programs. John, do you wanna? Oh, Kilian is looking at the list again.
No.
Yeah.
No, you can look at the list. You can look at the list.
John, go
Yeah,
ahead.
I think one. Maybe I'll start with a basic one. This is credit to Ofir for encouraging us to add it, but SQLite. Obviously, it's a very popular, very much used database. There is not a lot of the task instances in ProgramBench have existing external test suites. Like most of them come without a test suite of invocations. So that's where the innovation that Jeff and also, Parth gave lift on was really critical. SQLite happens to be one where there is an external test suite that Ofir found. And so in the paper somewhere we do comparisons of the coverage in terms of, the code pass, and there's some more, definitions there, but generally coverage of functionality that our test suites achieve versus the external ones. I think there's like 15 or 20, right, Jeff? Yeah. And I think we achieve very sort of comparable numbers there. So anyway, that's my favorite one.
SQLite, a
SQL.
database.
Yes,
Yeah.
yes.
Yeah, super complicated. Yeah, Kilian.
I'm going to go with the easier end of the spectrum again, because I really want to stress that even though ProgramBench as a whole is super hard, I think the fact that we're having almost 0 resolve rate, it tells us more about agentic capabilities than about the benchmark, to be honest. For example, very simple one, super useful rip grep. It's like kind of grep on steroids. It's super fast version of grep. And there's also stuff like FZF, which is like this terminal search ahead autocomplete kind of feature. Probably very simple.
Yeah, there were some I remember when we was talking with John. I mean, if there are computer architects here, I remember I told John if we could get Gem 5 in there, I think people would be super thrilled. But I even think for architects, building Gem 5 alone is like basically impossible sometimes. Probably my favorite is I used to do a lot of like static analysis work, compilers, and kind of like lexing for programming languages. So tree sitter being in there is a really fun one, and I think it's become also more interesting recently because a lot of people have started using that or like derivatives to kind of even build benchmarks or like AST parsing libraries. And so maybe if a language model can fix tree sitter and make it better, maybe we could build even cooler benchmarks. So.
Okay. Yeah, we have a whole suite of tasks. Some are super easy. Some are extremely hard. I think it's a great set of tasks. My personal favorites are, we put 3, I don't really understand much about biology, so I'm not going to talk about this too much, but there's 3 tools there that biologists use for sequence processing, so I think it's really cool. We also have stuff for like mapping software, just a very wide range of stuff, but the biology stuff is really exciting to me because it's just an amazing amount of breadth. Okay, moving on to the next question. Let's talk a bit about how ProgramBench is implemented. So a fun fact is that when we started working on ProgramBench, we were kind of thinking a bit about the reverse engineering angle, and we wanted to actually give the agent access to the binary and kind of have it decompile the existing program. But then we decided not to do that. And we wanted to make sure that the agent would not be able to reverse engineer anything or kind of cheat. So Kilian, maybe talk a bit about how we lock down the binary, and then we can also go around and talk a bit about agents cheating and what we did to make sure they don't cheat.
Sure. Let me maybe start with the why. Like, why don't we want to have decompilation in there? I think the how is much simpler. And I wouldn't consider decompilation cheating in a classical sense, other than that we maybe in the prompt say, please don't do that, and if it does it anyway, that's kind of bad. But it comes down to the interpretation of the benchmark. We wanted this benchmark to be about programming from scratch or vibe coding, if you want. If you allowed decompilation, and the agent could just throw a decompiler at the binary and get like chunks of source code that can only like patch together and then works, it would kind of defeat the purpose. It would still be an interesting benchmark, but it would be like very much a decompilation benchmark. But we wanted this a programming from scratch benchmark. So that's why we don't have decompilation in there. How to do that is surprisingly simple. We weren't the first ones to do that either, but it turns out that in the Linux kernel, you can execute programs even without read access. So you can kind of do chmod -r, you remove the read access of the executable. As long as it has the execution flag, the agent can still execute it, which I think is very cool.
Cool. I guess I'll maybe dive into like the no internet access of aspect of this. So I'll motivate it and let Kilian and Jeff kind of talk about, extra motivations and how we enforced it. Early on in the process, I was actually more of an advocate for the model having access to the internet because I thought that was really important. That's how humans kind of develop. They do software engineering by looking on Stack Overflow, by looking at, meaningful references when they build out new things. And then we carried out the first set of experiments where the model is allowed to do pretty much the exact same setting, but with internet turned on. And what we found in the first pass was, we wrote in the prompt, please don't look at the source code on GitHub. And the model says, okay, I'll look at a fork of the source code because that's not the source code. And then we said, well, you shouldn't do that either. And it says, well, then let me look at, a Bitbucket or, Atlassian or a Git tree or something. That's not GitHub. So that counts as, a legitimate source. And we say, don't do that. And then the model says, oh, well, there's a compiled version of the binary, and then some of the artifacts of that are available locally. So let me just kind of copy over the local reference of the code. So what I'm getting at is that this is a terrible cat and mouse game. So I'll let kind of other folks extend on it.
Just before we give Jeff a chance to also talk about this, there's a difference between no internet access and the model finding compilation artifacts and then cheating by... Can you talk a bit about... So even once we disabled internet, the model was still finding ways to cheat by finding compilation artifacts. Do you guys want to talk a bit about that?
Yeah, I'll add a little bit. Thanks for pointing that out, Ofir. That's actually a really good point. Yeah, in programming in ProgramBench, 3 programming languages are primarily represented. So we basically have no Python repositories. Like all of the repos in ProgramBench are written in compiled languages, and the reasoning for that is fairly straightforward. You want it to produce a standalone binary. So this means like C, C++, Go, and Rust. The thing is, for example, when you do go build or cargo build, -- release or something, for Rust, when you run that cargo build command, it's going to put the binary in sort of, target / release / and then the binary sits there. But if you look under the target folder, you might see that sometimes sort of in the process of building the executable, that remnants of the source code might pop up. I think there's some stochasticity as well in terms of sort of where that is placed, or even under hidden files. So
Yeah, there's
I'll let
stuff in the
Kilian-
home folder. I think there's like all kinds of like caches for source code or compiled parts of the source code that are there. But
Do you want to talk about how we dealt with that and how we made sure it couldn't find the artifacts?
I mean, I think it's kind of like almost like an implementation artifact, like an implementation detail. I think in the beginning we kind of first built the reference executable in the container. Then we ran some cleaning script, and then we gave that to the agent to be like, now start rebuilding this. And I think no matter what we tried, there were always some kind of loopholes of leaking source code or something that that's left over. But now, essentially in ProgramBench, we start from completely clean containers in which never any compilation of the target executable was carried out. So they're absolutely clean. You cannot obtain any of the source code.
Jeff, any additional things on cheating behavior?
Yeah, I mean, John and Kilian talked about cheating at inference time when the agents are actually doing it. I think Parth and I, who worked a ton on test generation, I think on the test generation side, we even found, I think, because we wanted this to be building behavioral tests, and we really wanted this to scale across a large set of repos. Kind of, we did tasks like agents with generating tests, and kind of, we started with maybe very basic things of I wouldn't say it was hacking behavior per se, but for example, we just tasked an agent with hey, here's an executable. Can you generate comprehensive tests, just conditions in the prompt? And the agents would come up with things, I think, that look stylistically diverse, but maybe not actual code execution wise diverse or high code coverage. And then so we started kind of setting up this auto research style loop with code coverage as a metric to maximize. But then we started seeing other fun failure modes. I think one really fun one is some of these test generation agents building tests that would just kind of run a really complex workload and then check that the exit code was 0. I think this case it's pretty funny because technically this does follow the guidelines that we gave them. But from a test case perspective, we do really want to be making sure that we have side effects, be verifying side effects and stuff like that. And so kind of Parth and I spent a ton of time building some extra validation conditions on top, kind of doing regeneration, setting up adversarial loops to also maybe have agents check other agents' work. And so those kind of turned into the tests that you see in ProgramBench. So
maybe the last thing to say about the no internet thing, and that kind of follows from what Sean already hinted at with how difficult it is to actually define cheating behavior. In addition to all the forks and mirrors, there's the package indices, which contain the program probably that you want to implement. But if you block those, then also you can't download any dependencies. And the second thing is that it's a very fuzzy line between what a dependency is and what the actual program is. There's some programs that essentially are split in the repository in 4 sub-packages. Are those now dependencies or not? Or what if I have, a Rust port of a C++ project? Is that now, the same thing? Or is that cheating to look up the Rust version of the same project? So it's just very, very hard to define. And for benchmark, we want to be as clear as possible in the guidelines.
I'll add something really quickly. The last thing we did was this sort of ambiguity that Kilian highlighted. We decided to see if language models could vote properly on this. So in one version of the benchmark, we have yes, internet. We still say, A, B, C, D, E, F, G are disallowed. And then at the very end, we have a pool of 9 language models.
Yeah, I think it's 3 different models.
3 different models invoked 3 times, yeah. Where they're given that list of prohibited things along with the entire trajectory or all of the actions, and they're asked did the model cheat in the inference run? You don't get a very clean set of votes. It's a very divided jury where 5 of them are saying, this looks okay, and then the other 4, if it's 5 and 4, that implies that one model is also kind of flip-flopping whenever you ask it. So yeah, I think even just sort of doing this LM as a judge style cheating defense, it's not reliable. Yeah.
Yeah, I just want to kind of make a summary of everything we've said here. So, the main benchmark is about getting agents to re-implement a program from scratch, and they found all kinds of very interesting ways to cheat. Some involving the internet, some involving artifacts in the Docker containers that we gave them. We patch a lot of those up. I'm sure some new ones will come up, and we'll patch those as they come in. And then the part that Jeff was talking about, and that Parth really helped us on during the development of this paper, was that we also use agents to generate the test suite. So we have this really cool agentic system that we developed for this project for writing tests to check if the submitted program and the original program that we asked the agent to implement, we have this huge test suite for checking if they're identical. And we had agents write all of those tests, and some of them also kind of cheated or were very lazy there. So there were kind of two types of laziness and cheating that we kind of had to contend with. And we made great progress, but I'm sure that as time goes by, we'll make these systems even better.
Well, one thing to also know, I think John mentioned this earlier, of like some of the instances, I think maybe some of the easier ones don't have external test suites. The ones that do, I think Parth and I spent a lot of time also making sure those tests kind of are added into our implementation system. So I think if anything, for a lot of these more difficult ProgramBench instances, the tests that we generate are almost purely additive in terms of making kind of evaluation of possible generated executables more rigorous. So that's kind of like how we thought about things for.
Yeah, and maybe last word on tests, it is we are committed to, you can add both tests if you're really overlooking some behavior. We are open to add tests to increase coverage. If there's tests that for various reasons are deemed unfair or impossible to solve, or they are just flaky because they have some randomness inherent to them, we kick them out. So that's part of developing ProgramBench. I think we have converged mostly. There's probably going to be some small patches to make this as informative as possible.
Yeah, one thing I'll add is that we've all developed benchmarks, and what we've noticed is that, or one thing that I've learned is that benchmarks aren't a static, finalized thing. I think a lot of people think, oh, you put a benchmark out, that's it. We're going to keep on using this code forever. But what we saw with SweetBench is that we actually kept on modifying and improving the benchmark over time. It was a real living thing. When we launched SweetBench, it had 2,200 tasks, and it took a long time to run on all of those. And so OpenAI worked on kind of filtering those 2,200 tasks into a subset of 500. We called that SweetBench Verified. And so we had like this new subset. And throughout this entire time, we were making improvements to the infrastructure. So benchmarks are a living thing. We adapt, we change. The agents become better at cheating. And so we have to adapt and create new ways to kind of block them from cheating. A lot of people think that it's that if they find, a single bug in the benchmark, that means the benchmark is dead. But that's not how it works. If you find a bug, you can tell us and we fix it. And the benchmark still works. And that's kind of how you make a good benchmark, is by continuously listening to feedback and changing it and improving it over time.
Maybe about that, I think it's also important to point out that the main metric of ProgramBench is fully resolved tasks, and maybe that's a separate question of why we strongly believe that this is the only metric we want to see in the long term. In the short term, we have this kind of almost resolved metric, which is a little bit more lenient, just so we get like a much so that we can rank the models and they just don't all score 0. But if you're developing models or you're training things, there's much more fine-grained signals in ProgramBench that you can look at. just important that those are not the main metrics as a benchmark, right? Because we want the metric to be very easily interpretable, and we really believe that only the fully resolved metric, that's the only clearly interpretable metric. Everything else, that could be a stopgap measure, or could be for you to get, signal on comparing different models, but it's not, the main metric.
So we have 18 more minutes before we have to go. So first of all, if you're watching this now on Twitter or YouTube, you can write a comment and we will try to kind of look at some of those. So if you have any questions, feel free to write them. If you have my WhatsApp number, feel free to text me. I kind of have a vaguer question now, and you guys can say whatever comes to mind. But I guess either during the development of this... Feel free to write them. Sorry. You're good. Either during the development of this project or with the end result that we put out, I guess what surprised you the most? Yeah, who wants to start?
I mean, that's going back to the cheating, but I think the ability of models to cheat so well was surprising. I think there was one, this goes back to the internet thing. There's one model that actually cheated that realized it was already in the no internet setting. It realized we had no internet during inference.
Yeah, that was
and then it was like,
crazy.
Well, but maybe there's internet during evaluation, and it just kind of sneaked in like a lot of like downloading commands, into its artifact, betting that during evaluation there's going to be internet access, and it can get through with that. So we still have some fixes around that hopefully will come very soon.
So just to explain and tell me if I'm getting this wrong, we first run inference on the agent where it must write source code, and then the script called compile.sh, which we run to compile its source code and produce the binary that we then test. And what the agent kind of hypothesized, it was like, okay, so I can't access the internet right now, but when they grade me, I might have internet access. And so in the compile.sh file, it like wrote all this stuff that like gets the program from the internet because it knew the URL by heart. And then when compile.sh ran, we did have internet on that server, and then it downloaded the right files because it got the URL 100% right, and it compiled them. And then I think the reason we caught it is because it got a 100% test pass. Is that it? Why we caught it?
I don't know. We still internally run a lot of like cheating detections and a lot of annotations on things, just so we're kind of ahead of the curve with any new behavior.
Yeah.
I think right now in the public version, evaluation might actually still run with internet, so that's something we'll patch pretty soon. So I've only seen this once. I'm not sure if it was actually successful, the model with that attempt at cheating. But you have to stay vigilant. If you find something that you feel like that's not right, please open a GitHub issue. It's a long game, right?
We have to make sure the transcript of this doesn't go into the training sets, because then they're going to know like this crazy, this way to cheat. So we're going to be deleting this podcast as soon as it goes live. John, do you have
more surprising things?
More surprising things.
Yeah, I think Kilian's example definitely takes the cake. As a team, we invested a lot in the analysis and just kind of understanding like what was going on.
That was mostly you, to be honest.
Group effort, I think this is perhaps a little bit less surprising, but for me, just as a benchmark person, it was really great to see, because SweBench in many ways is not discriminative as much as it was before, not just in terms of performance, but also in terms of behavior. Like SweBench instances, 15 to 30 turns, you'll probably get like most of them, and models are already getting most of them. With ProgramBench, what we saw is that the Claude models compared to the GPT ones take just a completely different range of turns. So the limits that we set on the agent in terms of inference runtime, quote unquote, is that they get up to 1,000 turns and 6 hours of wall clock time. the agents in like 99% of the runs don't exhaust either limit. So the agent is voluntarily submitting the solution. We did not see that, oh, these scores are low because somehow we're cutting off the agent too early and like we're just kind of artificially reducing their capability. They're all submitting sort of out of their own accord, per se. The GPT models take, I think, maybe like 40 to 70 turns, like as a general range. So it was a little bit entertaining to kind of see like GPT, I think 5.4 say like, oh yeah, I got FFmpeg done in like 45 turns or something like that. I will say GPT 5.5 is quite impressive, like because it's the current number one on the leaderboard. But I won't like ramble through all of them, but I think just it really does elucidate much more effectively than at least SweetBench what these models do in terms of their development behavior. Are they sort of like, for GPT, it kind of probes a lot in like the first 80% of turns, and it uses that to almost kind of like figure out what the complete specification is. And then you see in the remaining 20%, it essentially just tries to like one-shot the code base with a little bit of verification. Claude seems to be a little bit more interwoven. It'll probe and then implement and then double check and then do another round of probing. So I think that was quite interesting.
Yeah, I think for me, I think John had like found some of these conclusions in the earlier Code Clash paper, but I think like not only like if you think about SweetBench instances, right, there are only a few lines of code modified, and so I think that when we're like talking about coding agents, it's very easy to conclude that like, oh, these models like they kind of just program like a human. I think ProgramBench, looking at the trajectories or like the consequent repositories they generate, it's like very clear that I think they very clearly generate repos that don't look at all like kind of like they're underlying. But two, it kind of exposes a little bit things I think are like under quantified, but like I think for a bunch of years we've been talking about like good software engineering practices, good code base organization, and kind of coding agents right now I feel like are enjoying the benefits of that, of like probably human laid effort. But I think as people start to generate code bases more, like I always wonder maybe for ProgramBench, like if you had to do more work on like GPT's best attempt, would that even be possible, or like would that be too expensive? I think like it also goes to show I think ProgramBench is like a really good test bed to start exploring some of these ideas, right? Now that you have like rigorous infrastructure for actually validating executable and then like grading how much progress towards 100% FFmpeg or close to it you have, then you can start exploring these questions. And I think that's like the other, as much as benchmark should be like single metric improving capabilities, it also helps show like kind of like attributes or like qualitative features that kind of we haven't found a way to characterize yet until building one.
Yeah, sorry, go ahead, Kilian.
Wait, I actually realized like what I found was the most surprising thing is, and it was just that when we launched that it was 0%, because we did not. I think John did most of the collection of all these programs, and this was not selected by difficulty. It was not like, hey, let's find the hardest, weirdest, strangest executables out there. No, it was just very loose criteria. And as I hinted at before, there's some very simple ones in there. The fact that it's just 0% and now I guess 0.5% resolved, I did not expect that. And it's very interesting because, again, I think that tells us more about AI than it tells us about the benchmark. It tells us more about the models than about the benchmarks in many ways.
Just two high-level comments, I guess. With Human Eval, 4 or 5 years ago, we were trying to write like, single functions that were a few lines of code. With SweetBench, we're now inside these huge code bases, and we're fixing a real bug or developing a real feature, but it's kind of one contained thing, and everybody's been training on that type of stuff. And so these models are okay if you ask them for one very focused, kind of more well-defined thing. But if you ask them for something slightly bigger, they kind of get lost or they do silly stuff. And so I think the motivation behind ProgramBench, it's not necessarily that we think that replicating existing programs is the most important thing in the universe. We just want to kind of formally define a kind of real worldish task that is super long horizon and that kind of has a clear goal and that we can kind of leave agents to autonomously try to deal with. And we think that a lot of good is going to come out of trying to do better on this task. We do understand that kind of reproducing a wholly working program is not something that is commonly done, but we see giving this like program to the agent more of like giving it access to a product manager where it can kind of ask, okay, when I implement this feature, how do you want it to be? So instead of just asking that to a human, it asks it to a terminal program, it gets an answer, kind of develops something, and then it's like, oh, and when I give it this argument, what should the output be? And this kind of back and forth, we think we think that kind of optimizing towards this task will lead these agents to be much more capable, autonomous software developers, and in general, software developers that are able to deal with gigantic challenges. So that's the first thing I wanted to say. Kilian, remind me, what was this? You just made a comment, and I wanted to follow up on that too. The most recent comment that you said. Oh, Lord.
Made too many comments.
Yes. What was the other thing you talked about?
Oh, the most surprising thing we didn't select for difficulty.
Oh, yes. When we were building this, I kind of wanted to make it a bit harder. And so I was kind of, looking around for harder repositories to add. And then I was kind of thinking about maybe the super simple things we should remove. And so I was going through the repo and I found C-Matrix, which ended up being that first repo that GPT 5.5 solved. So C-Matrix, it's just a terminal program that when you invoke it, it kind of makes an animation in your terminal that looks like the Matrix animation. So it's just a very simple
It's
like
like a screensaver.
Yeah, it's
Like a screensaver,
It's like an ASCII screensaver. It's super simple. It's probably like 800 lines of code or something. It's really, really simple. And so I went up to John and I was like, hey, dude, we should remove this. Is really silly. Like all the agents are going to be able to do this right away. And John really wanted to keep it, which was a great decision. And I was wrong about, I thought that all the agents would like totally get that like one shot, like right away. And that ended up being not true. So yeah, it's really important to have a gradient. But I do think that, this gradient does make like tracking progress on ProgramBench slightly harder because I do think that we will kind of hit like 25% solved relatively quickly, and so people will think, oh, if we hit 25% in 2 months, we're going to finish this whole thing in like 6 months or something. But it'll actually start getting harder and harder as you solve more and more of the easier ones, which is kind of the same thing that happened in SweBench. Like going from 10% to 20% was like, I don't know, a month or two, but going from 80 to 90 took a while.
Yeah, I mean, SweBench had all these issues that told you the solution in the issue.
Yeah,
and
so the
agent couldn't solve it.
Yeah. So SweBench also had these extremely simple issues, but it took a while for the agents to solve them.
And I think that goes back to the metric. This is why the primary metric is in the space, like is on the how many instances do you resolve, or for now, I guess, almost resolve. It is so that this is like kind of very reflective and very easy to interpret. Versus if you ask about like what's the mean amount of tests that you solve on average, that's heavily skewed because there's like a lot of very simple instances where, solving, 90% of tests, that means, almost nothing. So that's why, we feel very strongly about these two metrics. There's also a whole section on the homepage with Q&A that talks about metrics and stuff, because that question comes up the most, I think.
Do you guys have any other comments before? I have a few final questions, but any other thoughts? Okay, so I don't want to spend too long on this, but I do regret that we didn't kind of write this down for SweBench, like predictions for where we're going to be in terms of solve rate. Just so, I don't know, somebody can clip this in a year and make all of us look silly. So should we go around and say where we think, what's, 1st of November, that's a good date, might be my birthday, but where do we think ProgramBench is going to be on almost resolved? Because I think fully resolved is too hard to quantify, but almost resolved November 1st and then almost resolved in a year from now. Do you guys want to make any predictions? And this is like frontier models with like, you know, $200 budget per task. Like, I don't want to go because I think we do have to define it in terms of like a budget, right?
Yeah.
So $200 per task. Frontier models, let's say 12 hours per task.
It's still 40,000 for the benchmark.
Yeah, it's super expensive. And also $200 in a year is going to get you what, like, you know, $2,000 gets you now. But where are we going to be in terms of this is I don't know if this makes any sense to do this, but yeah, if you guys want to
I think we should talk in terms of fully resolved, like, because we're going to clear out all of the remaining issues with the tests. Like, one of the reasons right now we have this almost resolved is that there might be a couple of bad tests. We're removing them, you know, in on that timeline. Certainly by then, like, the tests will be all good. Yeah.
Okay.
Yeah. Okay, I'll take the first stab at it. By November 1st, that's like, so June, July, August, September, 4 months from, 5 months. Or, yeah, 5 months from now. ProgramBench task collection is not too tricky, like compared to something, you know, where like you are asking people to create the problems and whatever.
Yeah.
So I think I have kind of like two answers on this. First is sort of a more data-pilled approach to this. You know, our team collectively, whether it's like SweBench or SweEfficiency, has built benchmarks in a way that is quite conducive to, you know, creating more task instances. And I think we also collectively believe that this is something that is important and good design, because I would say that's exactly what led to so much rapid progress when people figured out, oh, that SFTing and RLing on these environments is going to work. So I would guess, it's a little bit arbitrary, but to me, I think like we have some difficulty labeling in the project, and I would say it's about like maybe 50 to 60% of tasks are medium, like 10% are easy, and everything else is hard. So I think we'll probably get all the easy ones. Maybe it's a little bit random, maybe a fourth of the medium ones. 25% sounds a little bit low, but that's 50 instances out of 200. Yeah, maybe I'll stick with that. 25%.
So 25% by what date?
By November 1st.
And then
I think,
in a year from now.
In a year, I think. Yeah, I guess this is a little far out. To kind of Jeff's point, a lot of the code bases, the models right now are very monolithic. They're all kind of collapsed into one file. There's not a lot of file organization. I think that's sort of a characteristic that I don't know if it really needs to be adjusted. In one world, I could see like models can just do, you know, whatever they're good at. There's no need for organization. There's no need to really infuse taste or sort of, you know, software engineering best practices. It's just going to get it, in which case maybe the score is at like 60, 70%, you know, in a year from now. Yeah. I think it's just like the remaining couple, like FFmpeg seems a little bit scary to me. So I think that.
But FFmpeg, we also, I guess we need to write more tests.
Yes.
So if our testing scales as well as, you know, programming scales, which I guess it would, then FFmpeg might still be hard. But if we don't update the tests,
then
FFmpeg,
maybe it's a little bit of a moving target. But that's what I would say.
Kilian?
This is super hard, because I guess there's not only the models that people might throw like more specialized scaffolds at them. We didn't talk about this, but you know, our results are kind of like a baseline for kind of a very unopinionated single agent system. Doesn't mean that if you throw a multi-agent at it, it's going to immediately solve everything. Like, we tested that to some extent internally. I think it's not going to be that much. Okay, I'm going to say 15% in November and 50% in a year. I think it's going to take some time for this maybe to take off a little bit more. but I don't know. The error bars on this are, I'm a physicist, so I like error bars. I think the error bars eclipse the spectrum of answers I can.
Yeah, I'll take the midpoint of John and Kilian for November, just so I can hedge a little bit.
Nice.
I don't know. I think the formulation of ProgramBench is like we were able to add upstream tests. We were able to generate our own. I'm still very biased towards maybe like a performance or just kind of like code base quality. Like I do think one of the reasons why I don't think for agents it matters, but I do think one of the reasons why code base organization matters is because it's a way of scaling. Like when code becomes free, it'll help scale human supervision over code. And so I do think like it's possible. Maybe I don't think you'd ever add a test for it, but I do think like there's definitely some libraries in ProgramBench that I do think when you consider like recreating that library, you almost consider performance as a first party. And so I imagine there's probably at some point when the models get too good at correctness, maybe we should start adding performance tests. But I think that if we're looking at correctness only, I do think like somewhere along like 20% by November seems pretty reasonable, especially given some of the easier instances that are in the set.
I'm going to make up for my. So I thought that it would take 5 to 10 years to solve SweBench. I can't remember exactly, but I think I thought at least 5 years to solve SweBench. So I'm going to now go the opposite direction, and I'm going to say 30% by the 1st of November, 2026, and then May 28, 2027, I would say 85%, 80%.
What's the wager for who's the closest?
It gets to keep the fox.
Okay, you get a fox. John, you want to go in 7 minutes, you said? It's 4 or 3. Okay. I guess so. There was one question from the audience, and feel free if you have any final questions. We can do a tiny bit of audience questions. But one person asked, all these programs are in the training set. Like, why does that still make the benchmark valid? Which is a question we also got for SweBench. So we're very well versed at answering this question. John, do you wanna? Who wants to answer this?
Yeah, sure. I think like contamination free is very elusive, and also it really doesn't manifest as concretely as we thought it would. Like when people sort of take a look at these benchmarks, SweBench had this exact problem when it even coming out of the gate. Models at this point are totally trained on all of the PRs, all of the issues, all of the repositories, and who's to say like different forks. Like it's probably seen Django like hundreds, if not thousands, of times, like in pre-training, and then maybe probably in post-training as well. Just because I guess like I'll answer a question with a question, which is like, then why isn't SweBench 100%? And I think that explanation also applies for ProgramBench. I think if models were actually super capable of just regurgitating exact source code that it's seen, then pretty much all coding benchmarks based on any form of open source real world data should all be 100% at this point. Yeah.
Kilian?
And the other thing is that we actually have a different inference setting currently used as an ablation in the paper. In which we forced the agent to pick a different programming language than the one that was used to build the original executable, which is, by the way, one of the really cool things you can do with ProgramBench. I think I actually talked about this already, that the agent can use a different language. But basically, we looked at how much the score drops, and it certainly drops a little bit. But not that much. Does it actually uniformly drop? I don't even know if it uniformly dropped.
It does drop a tiny bit, but the weird finding was that, so the Claude family of models dropped in performance. The GPT family of models improved in performance. Because basically they all started to decide to use Python when they couldn't write it in the original source code. And the performance actually went up.
Yeah. So, I think that ablation to shed some light on that question. And if we're ever at the point where we're actually really worried about this contamination angle, we could just make that the default setting for ProgramBench 2.0 or however you want to call it. And the way that language models work and how they are very different from humans is that I think it would almost completely remove contamination. Like if you ask them to pick a different language, I don't think they would be able to regurgitate. Like some people, I told this to, they were like, yeah, but what if it regurgitates and then it translates? And that's just not how language models work.
Jeff, any quick comments on memorization?
I mean, realistically, if you had f of mpeg encoded somewhere in the weights of a neural network, I think that would be interesting to me, anyways. But yeah, I think John and Kilian touched everything about contamination. I think a lot of these benchmarks feel like they should be completely solved. I think there maybe is some aspect of like maybe in the agentic setting, it's harder to regurgitate, and maybe that's like a straw man argument towards this. But yeah, I think we definitely expect to see models doing way better, and shows that there is some reasoning gap or maybe some elicitation gap. Both of those are kind of what ProgramBench is designed to evaluate, both like elicitation from, there's a lot of people working on like really cool harnesses and trying to kind of like pull the most out of a model, and then also like with Kilian's baselines on Minisui agent, like actually seeing how far can the model really push things. So there's lots to do. I think I don't think we'll be there anytime soon. So.
This cheating question is this regurgitation question is not the gotcha that people think it is. There's so many answers to it. First of all, when we develop a benchmark, it's less about the specific task instances. It's more about the idea and the recipe. The task instances almost don't matter. So now that we've made ProgramBench, you can take that idea and you can apply that to internal private code bases that have never been on the internet, and you can do the exact same thing there. And so that's one way to track contamination. The second thing is, of course, if contamination was such a big issue, we would be seeing models get to 100%. They're not. So that kind of is a hint that maybe contamination is not as big of a deal as you think it is. Seeing something once in post-training is very different than seeing it like, multiple times. Seeing something once in pre-training is very different than seeing it, a billion times in post-training. Just because you saw something, a bunch of times during pre-training doesn't mean that you'll remember it by the time you get to post-training, or that you will remember it so completely that you'll be able to reproduce the whole thing. So in our view, natural, real data from the real world is just so amazing and awesome in what it lets us benchmark that we'd rather have that and have 1 or 2% of our benchmark be due to contamination. 1 or 2% of the performance on our benchmark be due to maybe contamination, rather than use totally synthetic data, which just wouldn't lead for a very appealing benchmark. Do we want to briefly talk about our single agent system versus multi-agent baselines very quickly? Or do we want to wrap it up?
I mean, I can say a few words. Baselines are baselines. I think Minisui agent is a system that's generalizing incredibly well. It has performed well on many benchmarks, and maybe you've seen the recent days on Twitter with some new benchmark that performed actually better than some other companies' harnesses. That can happen. Doesn't mean they are bad. It just means that it's kind of unopinionated in a way that if you throw it at a new problem, it tends to do very well because you don't constrain the language model in any way. That being said, I personally think that multi-agent systems will probably be much better at solving ProgramBench instances, and that makes me very excited, right? Because so far for most coding benchmarks, that's not what we have seen. People have been throwing multi-agent systems on SwiBench for a very long time, and right now the best systems still are very, very boring in that aspect, right? And the same is true for many other coding benchmarks. So if ProgramBench was a benchmark that really shows a difference, that would be super cool. And that's why you have a baseline that stays the same, and then you can use that to measure how good the other systems are.
I'm very excited for multi-agent systems. I do think that we might reach a point in the future where multi-agent, like the single-agent systems, are going to be so good that they might do just as well as a multi-agent system. They might just be slower. But in terms of performance, I'm not sure that there would be any gap. But in the short term, I do think multi-agent systems will do better, and I'm excited to use ProgramBench to evaluate those approaches. Any last thoughts before we wrap up? okay, this is it. We're going to keep on updating ProgramBench. We're probably going to have a multi-agent baseline soon. We also have lots of other super cool, interesting benchmarks that are still totally unsaturated, starting from Code Clash with John and Kilian, and Sweefficiency, which is Sweebench, but for efficiently trying to make things run faster with Jeff. And those are all still totally unsaturated. And Sweebench still has a variant which is unsaturated, Sweebench multimodal, so we'll put that out soon. Okay. That's it.
Yeah,
Bye-bye.
that's great.
Thank you so much.
Thank
Bye.
you.